You join another water molecule, form hydronium, and then this molecule right here, in these cases, these are, well, in the case of chloride or iodide, these are halogens, but they're going to go and form negative ions, whatever's left over. Nitric acid, then you have sulfuric acid. You've probably heard of that, very strong acid. Sulfuric acid, and then perchloric acid. These are the strong acids. O4. And these are good to know because if you see them on a chemistry exam, you know that these are going to completely disassociate. And remember, we keep using this word acid. What does acid mean? It means that these are strong acids. These completely disassociate. And if you like Arrhenius's definition of what an acid is, they increase your hydrogen concentration because you're obviously when you throw this in some water, all of these new hydronium ions are going to be formed, and they're going to overall increase your concentration of them, and that's why they're called an acid. And now, if you went on the strong base side, by Arrhenius's definition, right? By Arrhenius's definition, a base is something that creates hydroxide ions or anions in water. So pretty much anything, if you look at the periodic table, anything here, any of your group 1 elements, and group 1 elements, your alkali earth metals, that's bonded with hydroxide. If you put them in water, the hydroxide pops off. So let me just ask you with lithium or sodium. So for example, these are strong bases. So if I take some lithium, let me do lithium hydroxide in an aqueous solution. This completely disassociates. No equilibrium here. This is a strong base. So what's it going to disassociate to? Well, the little hydroxide ion is going to pop off. That's going to be a minus. It's in water still. Plus a lithium ion right there. So this will always dissociate in water. The same thing as if you have sodium. Sodium's going to do the same thing. Sodium hydroxide in aqueous solution, one-way reaction. You produce hydroxide and some sodium cations. And so you imagine when you put these in water, this concentration is going to go up. It's just like what we did in Le Chatelier's principle, where we said, oh, what if you add some of this or some of that to an equilibrium reaction? Well, how do you add it? Well, in this case, you can add a strong acid or a strong base. Now, everything I've done so far, this is the Arrhenius definition, where an acid increases your hydrogen concentration, a base increases your hydroxide concentration. Now, that is what you're going to see 90% of the time, but there's a slightly broader definition out there, and that is and I don't know the correct, I always say just Bronsted, but if you don't have fancy fonts, it's spelled like this: Bronsted-Lowry acid or base, and I'll say, but if you have good fonts, there's usually this little cross in the O. So I mean Bronsted. Well, Bronsted-Lowry acid. And all of these would also be Bronsted-Lowry acid. But the broadening of the definition is an acid is a proton donor, and a base is a proton acceptor. So let's look at this definition and in the context of everything we've just done so far. So, if you live by the Bronsted-Lowry definition, what is a proton donor here? Well, this hydrochloric acid, let me look at this reaction right here. This hydrochloric acid is donating a proton to this water molecule, right? The proton, a hydrogen atom is just a proton. That's an important thing to remember because it has a hydrogen ion. Because if you get rid of its electron, it has no neutron. It's just a proton sitting in space. So this hydrochloric acid is donating a proton to this water molecule to make a hydronium molecule, and it gave it away. So this is a Bronsted-Lowry acid as well, just as it was an Arrhenius acid. Let's see the Bronsted-Lowry version of a base. Okay, a base is someone who proton acceptor. So this guy, he had this nice little relationship with this hydroxide ion. The hydroxide ion got disassociated, so you can kind of, and it becomes a little bit fungible right here. You can kind of say, hey, this guy accepted this positive charge, or he was, and you know, it's a little bit wishy-washy here because this isn't, you know, it's not like this someone gave it a proton. You can kind of think it as he actually gave away electrons, but you know, if you just look at the final product, okay, he's got a positive charge when everything was done. So you say, okay, maybe that's a Bronsted-Lowry base. Now you're saying, okay, well, why did people even make the trouble of defining a Bronsted-Lowry base when, you know, all of the Arrhenius acids and bases could also be Bronsted-Lowry? And well, that's because Arrhenius is you're always dealing with water. Everything's in an aqueous solution. But I drew an example here of a Bronsted-Lowry base. It doesn't have to be in an aqueous solution. So if you have acetic acid right here, that's what's in vinegar, plus ammonia, there doesn't have to be an aqueous solution. What happens? This hydrogen gets donated to the ammonia ion to make ammonium. So this becomes positive, becomes negative. It donated this this proton, right? And Arrhenius has nothing to say for this. Because everything he deals with is hydronium and water, but the Bronsted-Lowry definition works in this situation. Now, the last kind of, or the broadest definition, although, you know, there are all these definitions, but you're going to be 90% of the time good if you just know the Arrhenius definition and just know that Bronsted-Lowry and what I'm about to say right now also exists, and that's Lewis acid and bases. Lewis acid and bases. The acid, now Lewis cares about electrons. Bronsted-Lowry cared about protons.